Hello, and welcome to General Astronomy Lecture 2, The Ancient Views of the Heavens. Today we know that the Earth is a planet orbiting a rather ordinary star, and a galaxy of more than 100 billion stars that is in an incredibly vast universe. We know that the Earth, along with the entire cosmos, is in constant motion. We also know that on the scale of cosmic time, human civilization has existed for only the briefest moment. How did we come to learn these things? So that's what we'll look at today. Careful observations of the sky have been going on for many thousands of years. Astronomy has been called the oldest of the sciences because its roots stretch deepest into antiquity. Ancient civilizations did not always practice astronomy in the same way or for the same reasons that we study it today, but nonetheless had some amazing achievements. Understanding this ancient astronomy can give us a greater appreciation of how and why science developed through time. Interest in astronomy likely stems due to part of our fundamental curiosity, but ancient cultures also had discovered that astronomy had practical benefits for timekeeping, keeping track of seasonal changes, and navigation. One amazing example comes from the people of Central Africa. Although we do not know exactly when they developed the skill, people in some regions learned to predict rainfall patterns by making careful observations of the moon. The orientation of the horns of a waxing crescent moon, which is the moon that you see in this chart, relative to the horizon, varies over the course of the year. Primarily because the angle at which the sun's path through the sky intersects the horizon changes throughout the year. This orientation also depends on latitude. In tropical regions in which there are distinct rain and dry seasons, rather than the four familiar seasons at temperate latitudes where we live, the orientation of the crescent moon can be used to predict how much rainfall should be expected over coming days and weeks. So you can see on this chart here how dry season is typically from October to February, and rainy season is from March to September. And based on that, relative to the orientation of the moon, so how much it's angled to the left or to the right, they were able to use that to predict when the rain and dry seasons would be. So, a pretty remarkable achievement way back then. The impact of ancient astronomical observations is still with us in our modern measurements of time. The length of our day is the time it takes for the sun to complete one full circuit of the sky, because the Earth rotates in 24 hours. The length of a month comes from the moon's cycle of phases. So the moon's cycle of phases takes about 29 and a half days, so that's where a month comes from. The year is based on the cycle of the seasons. In other words, how long it takes us to revolve, not rotate, around the sun. The 7 days of the week were named after the 7 planets of ancient times. We didn't know of all the planets we know of now back then. So the 7 planets of ancient times, which were the sun, the moon, and the 5 planets that are easily visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. The ancient definition of planet, which comes from a Greek word meaning wanderer, applied to any object that appeared to wander among the fixed stars. That is why the sun and the moon were on the list while the Earth was not, because we do not see our own planet moving in the sky. So back then, they just considered any wandering object a planet, so that wouldn't explain why the sun and the moon are on there, because they appear to be moving through the sky. Several of the English names come from Germanic gods, which you can see here in this table. For example, our day Tuesday comes from the Germanic god Tu, Wednesday comes from Woden, Thursday from Thor, and Friday from Freya. So you can kind of see where some of these things are coming from now. In the daytime, ancient peoples could tell time by observing the sun's path throughout the sky. Many cultures likely used sticks and the shadows they cast as simple sundials. The ancient Egyptians, in fact, built huge obelisks, often decorated in homage to the sun, which were likely served as simple clocks as well. This ancient Egyptian obelisk that you see in the image, which stands 83 feet tall and weighs 331 tons, resides in St. Peter's Square at the Vatican in Rome. It is one of 21 surviving obelisks from ancient Egypt, most of which are now scattered throughout the world. Shadows cast by the obelisk may have been used to tell time. We can trace the origins of our modern clock to ancient Egypt some 4,000 years ago. The Egyptians divided daytime and nighttime into 12 equal parts, which is how we got our 12 hours of each AM and PM. The abbreviations for AM and PM stand for the Latin terms ante meridiem and post meridiem, respectively, which means before the middle of the day and after the middle of the day. So you're starting to see that everything has these astronomical roots. Many ancient cultures built structures to help mark the seasons. Stonehenge is a well-known example that served both as an astronomical device and as a social and religious gathering place. The sketch on the right shows how archaeologists believe that Stonehenge looked upon its completion at about 1550 BC. Several astronomical alignments are shown as they appear from the center. For example, the sun rises directly over the heel stone on the summer solstice, so the first day of summer. So Stonehenge is actually much larger than what we typically see in photos. Most of it has been deteriorated over time, but you can see, for example, that on the first day of summer, the sun will align directly over this heel stone. And there's lots of other alignments as well. So it's amazing that even way back then, they were able to determine these things. In the Americas, one of the most spectacular structures was the Templo Mayor in the Aztec city of, I always say this wrong, I can't say it, I'm sorry. This is going to happen a few times. But it's modern-day Mexico City. So pardon me for not being able to pronounce some of these words. It features twin temples on a flat-topped pyramid. From the vantage point of a royal observer, watching from the opposite side of the plaza, the sun rose through the notch between the temples on the equinoxes. So that would be the fall and the spring equinox. Before conquistadors destroyed it, Spanish visitors reported elaborate rituals at the Templo Mayor, sometimes including human sacrifices that were held at times determined by astronomical observations. So, happy thoughts. This actually happens quite a lot in the class. We'll have a lot of these happy thought moments, but yeah, we'll get through it. Many cultures aligned their buildings and streets with the cardinal directions, north, south, east, and west, which made it easier to keep track of the changing rise and set positions of the sun over the course of the year. This type of alignment is found at such diverse sites as the Egyptian pyramids, the Forbidden City in China on the right image, and among the ceremonial kivas built by the ancient ancestral Pueblo people of the American Southwest. I believe that one's in New Mexico there in the center. This large structure, more than 20 meters in diameter, is a kiva in Chaco Canyon, New Mexico. Got ahead of myself. It was built by the ancestral Pueblo people approximately 1,000 years ago, and its main axis, which you see kind of pointing from the top left to the bottom right, is aligned almost precisely north-south. Other structures were used to mark the sun's positions on special dates, such as the winter or summer solstice. Many such structures can be found around the world, but one of the most amazing is the sun dagger, made by the ancestral Pueblo people in New Mexico. These large slabs of rock lie in front of a carved spiral, which you see there on the left and the right, in such a way that they produce special patterns of light and shadow at different times throughout the year. For example, a single dagger of sunlight pierces the center of the spiral only at noon on the summer solstice, while two daggers of light will bracket the spiral at the winter solstice. So here you see that summer solstice where the light at noon will pierce the center of the circle only on the summer solstice, the first day of summer. And then here on the right, on the winter solstice, you see the two lines of light bracketing that spiral only on that day. The sun dagger may have also been used to mark a special cycle of the moon that had ritual significance to the ancestral Pueblo people. The rise and set positions of the full moon vary in an 18.6-year cycle. That's the cycle of precession of the moon's orbit that we'll get into later. So the full moon rises at its most southerly point along the eastern horizon only once every 18.6 years. At this time, known as a major lunar lunar standstill, the shadow of the full moon passes through the slabs of rock to lie tangent to the edge of the spiral in the sun dagger. Then, 9.3 years later, half of that time, the lunar shadow cuts through the center of the spiral. The major lunar standstills can also be observed with structures nearby at Chimney Rock and in cliff dwellings at the Colorado Mesa Verde National Park. So it's incredible already that they can use this to mark the first day of summer and winter, but we believe that it could have also been used to predict the moon's motions over a 20-year span almost. It's incredible. Unfortunately, however, within just 12 years of the site's discovery in 1977, the rocks had shifted so that the effect no longer occurs. And we believe that these shifts were due to erosion of the trails below the rocks because of a large number of visitors. So we pretty much destroyed it. But still, at least we know what it is, and we have visual evidence of what it looks like. So it's a really remarkable feature. Before a structure such as Stonehenge or the Temple Mayor could be built, careful observations had to be made and repeated over and over to ensure their accuracy. Otherwise, how would they know to build them in that perfect way? Careful, repeatable observations also underlie modern science. Elements of modern science were therefore present in many early human cultures. The path that led to modern science emerged from the ancient civilizations of the Mediterranean and the Middle East, especially from ancient Greece. Greece gradually rose to power in the Middle East beginning around 800 BC and was well established by about 500 BC. Greek philosophers developed at least 3 major innovations that helped pave the way for modern science. First, they developed a tradition of trying to understand nature without relying on supernatural explanations, and of working communally to debate and challenge each other's idea. So this is a really big turning point. Up until this point, almost everything was believed to be supernatural, but now they take away that supernatural influence and they debate and they talk to one another. So this was really the birth of modern scientific community. Second, the Greeks used mathematics to give precision to their ideas, which allowed them to explore the implications of new ideas in much greater depth than would have otherwise been possible. So now they're adding math into the equation. Third, while much of their philosophy actively consisted of subtle debates grounded only in thought and was not scientific in the modern sense, the Greeks also saw the power of reasoning from observations. They understood that an explanation could not be right if it disagreed with observational facts. So this is very important. All 3 of these. The community, the use of math, and then the reliance on observation. This was really the beginning of the birth of modern science. So, taking this now and taking a look at what the Greeks came up with to describe the universe, we start here with our own solar system. They had a way to describe our solar system that we call the geocentric model. The Greek geocentric model of the cosmos, so named because it placed a spherical Earth at the center of the universe, developed gradually over a period of several centuries. Because this model was so important in the history of science, let's briefly trace its developments. So we're going to spend the rest of this lecture really taking ourselves from nothing to this model. How did we get to this point is basically what we're looking at. So this geocentric model places the Earth at the center of the universe, hence geocentric. And it's comparable to a merry-go-round, as you see on the left. So you could consider the Earth to be the center, the axis of that rotating merry-go-round, and then perhaps the children on the rides as the planets are moving around that center. So the first thing I'm going to show you now is actually a timeline. It's 2 slides because it couldn't fit it on 1 slide. This is a timeline of all the important people that led us to that geocentric model. Now, I'm not going to sit here and just list them all off. We will go through most of the important people in the coming slides. So I put this in here simply for you to reference. It's a great resource. So here's the other half of it. It's a great place to look if you just wanted some quick information about who did this or when did this person do that. But we will go into detail with some of these people now. So these slides just serve as a reference. So I'm going to go back a slide. So we're going to begin at the top left. We're going to begin with Thales. We generally trace the origin of Greek science to the philosopher Thales. Thales was the first person known to have addressed the question, what is the universe made of, without resorting to any supernatural explanation. His own guess, that the universe fundamentally consisted of water and that the Earth is a flat disk floating in an infinite ocean, was not widely accepted even in his own time. Nevertheless, just by asking the question, he suggested that the world is inherently understandable and thereby inspired others to come up with better models for the structure of the universe. So even though he was very incorrect, as we know today, and not many people believed him, it was still a big turning point in astronomy. Next is ANAXIMANDER. A more sophisticated idea followed soon after, proposed by a student of Thales named ANAXIMANDER. He suggested that Earth floats in empty space, so we're making progress, surrounded by a sphere of stars and two separate rings along which the sun and moon travel. We therefore credit him with inventing the idea of what we will call the celestial sphere. You'll hear me talk about that a lot once we get through this history lesson. Interestingly, Anaximander imagined Earth itself to be cylindrical rather than spherical in shape. Now that sounds odd, but think about this. He probably chose this shape because he knew Earth had to be curved in a north-south direction to explain changes in the constellations with latitude. Because the visible constellations do not change with longitude, he saw no need for curvature in the east to west direction. All right, so as you travel north to south along the globe, what you see in the sky in terms of constellations changes. But if you travel, say, from Durant, Oklahoma, straight east or west, you'll see the exact same constellations. So it's kind of reasonable that he thought curvature was only along one direction. So to assume the Earth was cylindrical, even though it seems weird, is actually not too inaccurate to think about back then. All right, next we have Pythagoras. We do not know precisely when the Greeks first began to think that Earth was round, but this idea was taught as early as about 500 BC by the famous mathematician Pythagoras. He and his followers envisioned Earth as a sphere floating at the center of the celestial sphere. Much of their motivation for adopting a spherical Earth was philosophical. The Pythagoreans had a mystical interest in mathematical perfection, and they considered a sphere to be geometrically perfect. So they believed that we were the center of everything, we were perfect and all that. So they thought that the Earth was spherical, not because it was an observational fact at the time, but because that was perfection and that's the way they viewed it. So it's pretty amazing that it could be so simple. Next is Plato. The Pythagorean interest in heavenly perfection became deeply ingrained in most Greek philosophers. So that idea really, really held on for a long time, as you'll see as we go on. It took on even more significance after Plato asserted that all heavenly objects move in perfect circles and at constant speeds, and therefore must reside on huge spheres encircling the Earth. So not only now do we think the Earth is a perfect sphere at the center of everything, but we believe everything else moves in perfect spheres at perfect speeds around us. The Platonic belief in perfection influenced astronomical models for the next 2,000 years. Of course, those Greeks who made observations found Plato's models to be problematic. The apparent retrograde motion of the planets, which we'll talk about in a second, is the backward motion of planets in the sky, already well known by that time, clearly showed that the planets do not move at constant speeds around Earth. So there was already some issue with this idea. An ingenious solution came from Plato's colleague EUDOXUS, who created a model in which the sun, the moon, and the planets each had their own spheres nested within several other spheres. Individually, the nested spheres turned into perfect circles. By carefully choosing the sizes, rotational axes, and rotation speeds for the invisible spheres, EUDOXUS was able to make them work together in a way that reproduced many of the observed motions of the sun, the moon, and the planets in our sky. Other Greek models refined the model by comparing its predictions to observations and adding more spheres to improve the agreement. So here in the top you see what we call that retrograde motion. So in the sky, this is, for example, the path of Mars. At the beginning of January, it starts over here and moves from west to east throughout the months. But then, for a little while, it moves apparently backwards through the sky. That's that retrograde motion I mentioned. And then it continues its path from west to east. So that was a challenge to this perfect circle idea. So EUDOXUS came along and started to come up with some ideas of these nested spheres, which we'll get into more in just a moment. Following EUDOXUS is Aristotle. Whether EUDOXUS and his followers thought of the nested spheres as real physical objects is not clear, but Aristotle certainly did. In Aristotle's model, all the spheres responsible for celestial motion were transparent and interconnected like the gears of a giant machine. Earth's position at the center was explained as a natural consequence of gravity. Aristotle argued that gravity pulled heavy things toward the center of the universe and allowed the lighter things to float toward the heavens, thereby causing all of the dirt, rock, and water of the universe to collect at the center and form the spherical Earth. I guess not a terrible idea back then. We now know that Aristotle was wrong about both gravity and Earth's location. However, largely because of his persuasive arguments for an Earth-centered universe, this geocentric view dominated Western thought for almost 2,000 years. To explain the apparent retrograde motion of the planets, Apollonius suggested that each planet moved around Earth on a small circle that turned upon a larger circle. The small circle is sometimes referred to as an epicycle, and the large circle is often called a deferent or deferent. So, two important terms. A planet following this circle upon circle motion that you can see in the schematic on the right would trace a loop as seen from Earth, with the backwards portion of the loop mimicking the apparent retrograde motion. So that graph that I showed you a moment ago with that retrograde motion, this could explain it. So this idea of a circle upon circles, so the idea is that the planet itself moves in a little circle, but as it's moving in that little circle, that circle as a whole is moving around a larger circle. So if you were to trace this out, it would form this little bit of a backward motion for some time before returning back to that west to east motion. So right there, you could explain the retrograde motion because of this idea. Among his many accomplishments, Hipparchus developed the circle upon circle idea of Apollonius into a model that could predict planetary positions. So this is the first time now that we are taking something that we see and using it to predict future positions. To do this, Hipparchus had to add several features to the basic idea. For example, he included even smaller circles that moved upon the original set of small circles, and he positioned the large circle slightly off-centered from Earth. So now, not only are we starting to predict things, but we're also slightly starting to move away from this idea of perfection by placing them off-centered from the Earth. So we're getting there. But the culmination of it all, of this geocentric model, comes from Ptolemy. Greek modeling of the cosmos culminated in the work of Claudius Ptolemy. Ptolemy's model still placed Earth at the center of the universe, but it differed in significant ways from the nested sphere ideas of Eudoxus and Aristotle. We refer to Ptolemy's geocentric model as the Ptolemaic model to distinguish it from the earlier models. So he has his own name now for this model, the Ptolemaic model. Ptolemy's great accomplishment was to adapt and synthesize earlier ideas into a single system that agreed quite well with the astronomical observations made at the time. So even though it was still wrong, what he put together agreed to a reasonable extent with the observations that were being made at that time. So he basically took everything and put it into one nice package. In the end, he created and published a model that could correctly forecast future planetary positions within a few degrees of arc, which means a degree of arc is a 60th of a degree, which we'll get into later as well. I can explain it too. I mean, it's also about the angular size of your hand held at arm's length against the sky. So right now you can hold your arm out all the way extended with your hand sticking up, and he could predict planetary positions within a few degrees of arc, which is the width of your hand. So that gives you an idea. This was sufficiently accurate at the time to keep the model in use for the next 1,500 years. So this geocentric model came together pretty quickly, relatively speaking, through all these different people, and then Ptolemy put it into one nice package where the Earth is at the center of the universe and everything moved around us. Even though it was incorrect, it was a way of explaining what they saw. So it was still great that they were using science to agree with the observations they were making. And that's a part of what makes science so tough sometimes. I mean, for thousands of years, they believed this was correct, and it did agree with observation. So, I mean, who knows, even today, we could be sure about something, and then in 1,000 years, we're going to find out that we were totally wrong. So we know that the Earth is not the center of the universe. So in our next lecture, we're going to talk about the Copernican revolution that takes us away from the ancient Greeks' model of the Earth-centered system, and it takes us to the heliocentric system, where the sun is the center of our solar system, which is in fact correct. So now we're going to start getting closer and closer to modern science. So, as always, thanks for watching, and I'll see you in the next lecture.